Takeoff is the phase of flight in which an aerospace vehicle goes from the ground to flying in the air. For aircraft that take off horizontally, this usually involves starting with a transition from moving along the ground on a runway. For balloons, helicopters and some specialized fixed-wing aircraft, no runway is needed. Takeoff is the opposite of landing. Horizontal takeoff. Power settings for light aircraft. Usually full power is used during takeoff. Large transport category aircraft may use a reduced power for takeoff, where less than full power is applied in order to prolong engine life, reduce maintenance costs and reduce noise emissions. In some emergency cases, the power used can then be increased to increase the aircraft's performance. Before takeoff, the engines, particularly piston engines, are routinely run up at high power to check for engine-related problems. The aircraft is permitted to accelerate to rotation speed. The term rotation is used because the aircraft pivots around the axis of its main landing gear while still on the ground, usually because of manipulation of the flight controls to make this change in aircraft attitude. The nose is raised to a nominal 5 degrees to 15 degrees nose-up pitch attitude to increase lift from the wings and effect liftoff. For most aircraft, attempting a takeoff without a pitch-up would require cruise speeds while still on the runway. Fixed-wing aircraft designed for high-speed operation have difficulty generating enough lift at the low speeds encountered during takeoff. These are therefore fitted with high-lift devices, often including slats and usually flaps, which increase the camber and often area of the wing, making it more effective at low speed, thus creating more lift. These are deployed from the wing before takeoff, and retracted during the climb. They can also be deployed at other times, such as before landing. The speeds needed for takeoff are relative to the motion of the air. A headwind will reduce the ground speed needed for takeoff, as there is a greater flow of air over the wings. Typical takeoff air speeds for jetliners are in the 130 to 155 knot range. Light aircraft such as a Cessna 150 take off at around 55 knots. Ultralights have even lower takeoff speeds. For a given aircraft, the takeoff speed is usually dependent on the aircraft weight. The heavier the weight, the greater the speed needed. Some aircraft are specifically designed for short takeoff and landing, which they achieve by becoming airborne at very low speeds. Takeoff optimization. A takeoff on any transport aircraft is with some amount of roll on the ground, during which the aircraft accelerates to the required speed at which the aircraft can safely leave the ground. Takeoff optimization is a process by which the maximum weight for a safe takeoff is calculated for a given set of conditions like runway dimensions, slope, elevation, winds, temperature, etc., along with the calculation of this maximum safe weight. An associated set of speeds called takeoff speeds is also calculated. The regulations specify that in a twin or multi-engine aircraft, the weight for the takeoff is to be calculated assuming that the critical engine will fail at the most critical instant during the takeoff. The takeoff weight thus calculated usually varies with different factors, and this weight is referred to as the takeoff performance limited maximum takeoff weight. Some of these factors are internal or related to the selections made on the aircraft. The internal factors mostly relate to the design features of the aircraft, the thrust, power output from the engine of the aircraft, utilization of high-lift devices like flaps, slats, boundary layer control and any other such aspects. Even if the runway conditions permit the aircraft to take off at a very high weight, the weight with which takeoff is being attempted should be restricted as below the maximum takeoff weight as certified for the model of the aircraft. The exact thrust available from the engine or being used from the engines will also have an effect on deciding the weight of the aircraft with which a safe takeoff can be attempted. Some specific malfunctions to some of the systems could be allowed during the takeoff as per the regulations, and the list of such malfunctions is listed in a document called Minimum Equipment List and Configuration Deviation List, which are approved by the regulator. However, some of these MELs or CDLs invoked prior to takeoff could have performance implications which could restrict the maximum weight with which a safe takeoff can be attempted for a given set of conditions. There are also many other speeds and restrictions applicable to the aircraft which would restrict the maximum takeoff weight. VMCG, VMCA, VMBE, tire limiting speeds, minimum unstick speed, etc. are some such limits. There are two other factors which have to be definitely considered related to the certified maximum zero fuel weight and the certified maximum landing weight. The maximum landing weight could sometimes get restricted to a lower value due to the low runway length or the high density altitude of the destination airport. The actual weight at the time of takeoff cannot exceed the performance-limited MTOW, calculated the sum of any restricted landing weight and the trip fuel and actual zero fuel weight plus the total fuel on board. In rare cases, if there are high hills on the route, that could pose an additional restriction. Regulations require that the aircraft should be able to clear the hills with a safe margin after suffering critical engine failure. VMCG is a calibrated airspeed at or below which, with the aircraft still on ground, if the critical engine fails with the other engine operating at the takeoff power, directional control cannot be maintained with the use of aerodynamic controls alone. To maintain directional control in such a scenario, either nose wheel steering or differential brakes or a combination of both will need to be used. Directional control in such a scenario is also possible if the power thrust on the other live engine is appropriately reduced, and in this scenario, with lower thrust power from other engine, the value of EMCG will reduce. The speed V1, which is called the takeoff decision speed, is to be selected in such a way that it is positively above this value. VMCA is a calibrated airspeed at or above which it is possible to maintain directional control after getting airborne with the critical engine failed and the other operating at takeoff power. Regulations allow a bank of 5 degrees into the live engine, which is considered as no bank, along with the full rudder to the same side, leading to an effectively side-slipping situation to maintain direction. The speed V2, which is referred to as the takeoff safety speed, is to be selected in such a way that it is positively above this value. In fact, regulations specify that V2 should be more than 1.1 times VMCA and the value of VR should be at least 1.05 times VMCA. VMBE is a speed that is dependent mainly on the capabilities of aircraft's brake system to absorb energy and the available runway length. After starting a takeoff roll on the runway with a particular all-up weight, if a reject takeoff is attempted at a speed above this, stoppage within the available runway length is not guaranteed. Of course, the density, altitude and the existing winds will have an effect on this value. The value of EMBE will reduce if the weight is reduced or if a brake system of better capability is installed. The value of E1 is to be selected as something below this, depending on the external factors like air density, runway length, runway slope, elevation, existing surface winds, outside air temperature, etc. The speeds will need to be varied to achieve the best performance. Operations with transport category aircraft employ the concept of the takeoff V speeds, V1, VR and V2. These speeds are determined not only by the above factors affecting takeoff performance, but also by the length and slope of the runway and any peculiar conditions, such as obstacles off the end of the runway. Below V1, in case of critical failures, the takeoff should be aborted. Above V1, the pilot continues the takeoff and returns for landing. After the co-pilot calls V1, she will call VR or rotate, marking speed at which to rotate the aircraft. The VR for transport category aircraft is calculated such as to allow the aircraft to reach the regulatory screen height of V2 with one engine failed. Then, V2 is called. This speed must be maintained after an engine failure to meet performance targets for rate of climb and angle of climb. In a single-engine or light twin-engine aircraft, the pilot calculates the length of runway required to take off and clear any obstacles. To ensure sufficient runway to use for takeoff, a safety margin can be added to provide the option to stop on the runway in case of a rejected takeoff. In most such aircraft, any engine failure results in a rejected takeoff as a matter of course, since even overrunning the end of the runway is preferable to lifting off with insufficient power to maintain flight. If an obstacle needs to be cleared, the pilot climbs at the speed for maximum climb angle, which results in the greatest altitude gain per unit of horizontal distance traveled. If no obstacle needs to be cleared, or after an obstacle is cleared, the pilot can accelerate to the best rate of climb speed, where the aircraft will gain the most altitude in the least amount of time. Generally speaking, Vx is a lower speed than Vy, and requires a higher pitch attitude to achieve. Normally ground speed for takeoff varies between 250 km per hour to 475 km per hour. Assisted takeoff is any system for helping aircraft into the air. The reason it might be needed is due to the aircraft's weight exceeding the normal maximum takeoff weight, insufficient power, or the available runway length may be insufficient, or a combination of all three factors. Assisted takeoff is also required for gliders, which do not have an engine and so are unable to take off by themselves. Vertical takeoff. Vertical takeoff refers to aircraft or rockets that take off in a vertical trajectory. Vertical takeoff eliminates the need for airfields. Most vertical takeoff aircraft are also able to land vertically, but there were certain rocket-powered aircraft of the Luftwaffe that only took off vertically, landing in other ways. The Bachem Bar 349 Natter landed under a parachute after having taken off vertically. Other late Third Reich projects, such as the Heinkel P-1077 Julia or the Focke-Wulf Volksjäger II, climbed to their ceiling at a nearly vertical angle and landed later on a skid. VTOL vertical takeoff and landing aircraft include fixed-wing aircraft that can hover, take off and land vertically, as well as helicopters and other aircraft with powered rotors, such as tilt rotors. Some VTOL aircraft can operate in other modes as well, such as a CTOL, STOL, and/or STOVL. Others, such as some helicopters, can only operate by VTOL, due to the aircraft lacking landing gear that can handle horizontal motion. VTOL is a subset of STOL. Besides the helicopter, there are two types of VTOL aircraft in military service. Craft using a tilt rotor, such as the Bell Boeing V-22 Osprey, and some aircraft using directed jet thrusts such as the Harrier family. Rocket launch. A rocket launch is the takeoff phase of the flight of a rocket. Launches for orbital space flights, or launches into interplanetary space, are usually from a fixed location on the ground, but may also be from a floating platform such as the San Marco platform, or the Sea Launch vessel.